Welcome back to the Deep Dive. For so many of you, that journey into electronics and the Internet of Things, IoT, it starts with these great ideas. But the hardest part is always bridging that gap, right? Going from just a concept to a, a functioning, finished product.
And that gap is exactly what we're tackling today. I mean, this whole deep dive is built from the core insights of some really specialized electronic design and IoT system workshops.
Okay.
So our mission for you is pretty simple. We want to extract that organizational framework and the absolute non-negotiable rules you need to step out of theory and into a job.
So you can be immediately employable in a serious startup or a core tech industry.
Exactly.
Okay, so let's unpack this blueprint. We're talking about developing a really full skill set here. This goes way beyond just simple circuit diagrams.
Oh, far beyond. You need to know how to select and use components. Everything from bare integrated circuits, ICs, to microcontrollers and sensors.
Right, but also how to debug circuits using proper lab instruments,
Yeah.
handle the mechanical side of things.
That's a huge part of it. Fabricating printed circuit boards, PCBs, building enclosures. The goal is always a fully integrated, polished system.
And what's crucial to understand, I think, is that success here, it starts with organization, not with a soldering iron.
100%. The workshops immediately set that expectation. You're working in a structured team, and they even tailor that structure based on your experience level.
I found the team sizes really fascinating because they signal right away what's expected of you individually.
They do.
So if you're a fourth semester student, maybe a bit newer to this, the team size is 3, and you stick to your own lab group.
Yeah, that size gives you a bit of a safety net. It maximizes knowledge sharing. But then if you're a more senior, say 6th semester student, the expectation is higher.
And the team size shrinks to 2.
It shrinks to 2, but your selection pool gets bigger. You can pick a partner from either of the 2 lab groups, which reflects a greater assumption of independence, of technical skill.
So fewer hands, but a wider choice of who to work with. It's also interesting how the evaluation changes based on that seniority. How does that impact the project itself?
Well, for the 4th semester students, they follow the newer NEP protocol, which means the evaluation is continuous. It happens all semester.
No big final practical exam.
None. So the pressure is on to deliver the finished product and all the documentation incrementally. You can't just cram at the end. If you fall behind, you're in trouble.
Now the 6th semester students.
They're still on the older protocol. Their evaluation all comes down to an end semester practical exam.
Which gives them a little more breathing room on the documentation, I guess, right up until that exam day.
A little, but the physical project still has to be 100% functional well before then.
Okay, so once that structure is set, the next logical question is, well, where do these ideas even come from?
Right. And the sources point out 2 equally valid approaches. Because remember, the mission is learning the process of building. It's not necessarily about pure from-scratch invention.
The first one is exploration.
This is that classic engineering mindset. You look at society, you look at your own home, you see a problem, and you design something to solve it.
The example they gave was brilliant. Automating the job of gate guards at a big university.
Yeah.
Instead of them manually writing down license plates, you design an IoT device that, it captures the image?
It captures the image, it extracts the plate number automatically, and then it immediately posts that data to the cloud. It's an immediate, tangible solution.
And the second approach?
Is adaptation. And this is perfectly okay. Since the goal is mastering the design process, searching the internet and adapting an existing idea is absolutely allowed. It lets you focus on the complexity of implementation, not the difficulty of coming up with a brand new idea.
So once we have that idea, whether it's automated license plates or something else, it's still this massive, intimidating concept. How do you break it down into manageable chunks?
This is, I think, the biggest hurdle for every new designer. You can't build it all at once. So to solve this, the workshops introduce something called the 6-box model.
And this is the core of the whole framework, right?
Yeah.
It's the visualization tool that forces you to categorize everything by function before you even touch a component.
Precisely. It gives you a clear structural breakdown for any system you can imagine. It maps out the device's logic. So let's walk through them. Box 1 is the input box.
So this is everything that pulls in data from the real world. We're talking about switches, keypads, that sort of thing.
Yes, or more complex things like environmental sensors for temperature, light, pressure. It's the eyes and ears of your system.
Got it. And that information flows into box 2.
Box 2, the signal processing box. This is the brain. It's almost always a microcontroller like an ESP32 or an STM32. It runs your code, it interprets the input, and it decides what to do next.
And that doing part happens in box 3, the output box.
Exactly. This is where the system actually affects the world. Could be visual, like an LCD screen or some LEDs, could be audio through a speaker, or it could be actual physical control.
Like motors or relays.
Right. Motors, solenoids, you name it.
Okay, so that's the core logic. Input, process, output. What are the other 3 boxes?
They're the support structure. Box 4 is the power supply box. Every single system needs one. And for portable or IoT projects, the rule is clear. It has to be battery powered. You can't just have it plugged into the wall forever.
That makes sense.
Box 5.
The communication box. Now, this is only for IoT devices, but it's the critical link that lets your system talk to the internet.
And finally, box 6. The host and storage box.
This is for data that doesn't just get displayed locally. It's where you might store data long-term or where you communicate with a host platform.
Like sending that license plate number up to a cloud server.
That's the one. That whole structure, it guarantees you haven't forgotten a fundamental part of your system design before you even start.
It's the blueprint that turns a vague idea into a parts list and a wiring plan.
Exactly. But the framework alone isn't enough. You have to follow some strict technical requirements. This is where the non-negotiables come in. Okay, let's start with the heart of the system, that signal processing box. What microcontrollers are actually recommended?
You're looking for platforms that are compact, that are built for integration. So the Arduino Nano, the ESP32, the STM32-based Blue Pill, maybe a Raspberry Pi.
But there's a big exception here. We have to talk about the Arduino Uno. It's everywhere for beginners,
Yeah.
but the source material says to actively avoid it in a final product. Why?
It really comes down to its form factor and its purpose. The Uno is fantastic for learning on a workbench. It's big, it's robust.
But it's clumsy.
It's clumsy for integration. The sources call it that specifically. The board is huge. Its USB connector is massive. And the headers aren't designed to be easily mounted inside a finished product. You want something smaller, like the Nano, or something with built-in connectivity, like the ESP32.
So it's a development tool, not a deployment platform. That makes perfect sense. I also saw there's a real incentive for showing total mastery here.
Oh, yeah.
Extra credit if you use a bare microcontroller chip instead of a pre-built board.
Okay.
You mean literally just the chip.
Literally just the chip. It means you have to design all the supporting circuitry yourself, the crystal, the voltage regulation, everything.
Wow. Okay.
That shows you understand the entire electronic ecosystem, not just how to plug in a module. Which brings us to probably the most controversial rule for beginners, the component rule.
The strictly no-no rule.
The strictly no-no rule against using those cheap, ready-made function boards you see online.
So why is this rule so strict? What are you actually missing when you just plug in one of those pre-made modules?
You're missing the learning. They hide all the learning. Every single one of those boards, a relay board, a sensor module, it has crucial support circuitry on it.
Things like voltage regulation, signal conditioning.
Filtering, impedance matching, all of it. If you use the bare IC, you are forced to learn how to design those support circuits. That is where the real engineering skill is. It's not just connecting 4 wires.
Yeah, that's a huge insight. The module might work, but you learn nothing about why it works, or more importantly, why it might fail.
Exactly. So no shortcuts, unless, and there is a big unless.
Okay.
The big unless is if the function you need just can't be practically implemented with bare ICs. For example, trying to design a Bluetooth radio from scratch is, well, it's incredibly complex. So a pre-made Bluetooth module might be allowed, but you have to justify it.
The burden of proof is on you.
Okay, so we've designed our system with the 6-box model. We've selected our components. Now we have to actually build it. What's the non-negotiable for the final assembly?
This is mandatory. Putting the finished circuit on a breadboard is simply not acceptable at all.
It's not a product.
It's not a product. A breadboard is for testing. It's not permanent. It's not reliable. The circuit has to be finalized.
So that means soldering it onto a 0 board, or probably creating a custom printed circuit board, a PCB.
Right. And the sources even suggest ways to do that. You can use a lab milling machine, or for a faster, cheaper option, you can use the toner transfer method. The key is the discipline of finalization. You're building a prototype, a product.
And a product isn't just a circuit board. It needs 2 more finishing touches. First, it has to have its own power. Absolutely, self-sufficient. It needs its own battery-driven power supply, especially for a portable or IoT device. And it needs a suitable charger. You shouldn't have to plug it into a lab bench to make it work.
And second, it needs an enclosure. A project is not complete until it has a box.
It has to look like a finished system. Whether it's a ready-made housing, a custom box you make with a 3D printer, or even just a simple wooden box, the device must be contained. You're delivering a complete prototype.
So we've covered the structure and the rules. Let's see how this all comes together. What are some of the innovative projects that really showcase this journey?
Let's start with a really complex one, an IoT idea that puts a lot of stress on that signal processing box. The Twilight-based streetlight control system.
Now, most streetlights just use a simple light sensor, right? They turn on when it gets dark. Why is this so much more complex?
Because it requires some serious computation. The microcontroller can't just rely on a simple light reading, which can be unreliable. Instead, it has to compute the precise moment of astronomical twilight for every single day of the year.
Wait, based on its coordinates? That's a lot of math for a tiny chip, isn't it?
It requires intensive floating point math and a very precise clock. It forces the designer to really optimize their code and understand the processor's limits. That's the kind of challenge that builds real expertise.
That is a fantastic application. Okay, what about something a bit simpler? A more domestic IoT system.
The visitor counter or busyness monitor. This is just pure utility. Imagine a guard at a store entrance clicks a button every time someone walks in.
The device logs the timestamp.
And the host and storage box then sends that data to the cloud, giving you a live graph of how busy the store is hour by hour. You can see your peak times instantly.
Let's move away from the cloud into scientific data logging. The temperature data logger.
Yeah, a portable device, something you could, say, stick under the hood of your car, run the engine for a while.
And then come back later and download the data to see the temperature profile over time.
Exactly. You milk out the data later. The engineering challenge there is all about the power supply and making sure the enclosure and the input sensors can handle that harsh environment.
For more precise scientific work, the source mentioned an automatic pendulum timer.
Yeah, this is way more accurate than a person with a stopwatch. It uses a precise input sensor, like a light gate, to measure the pendulum's period. The signal processing box has to be incredibly fast and accurate.
So you have to really understand interrupts and timing loops to get that right.
You have to master them.
Okay, let's look at the more creative side, the multilingual talking device.
Right, so you build, say, a digital thermometer, but instead of just showing the temperature on a screen,
It speaks.
it speaks. It has a speech synthesis IC in its output box, and it can cycle through readings in different languages like Hindi, Tamil, Telugu. That requires a really deep understanding of audio integration.
And lastly, two projects that lean heavily on the enclosure and the output. The electronic birthday blowout candles and the electronic hourglass.
Both of these were past student projects that used 3D printing to create these really novel polished enclosures, and they relied on complex LED sequencing for the display. It just proves that the final step, the finish, it's not an afterthought. It's integral to the whole thing.
That whole gallery really shows the complete journey, from the idea to the six-box model, all the way to a finished, enclosed, functional product. The goal of this whole process is to instill that professional discipline.
Which brings us to our final and maybe the most revealing requirement of all, the project report. It has to be written in a scientific document preparation system called LaTeX.
Often using a tool like overleaf.com. And this is not a simple word processor.
Not at all. It's a rigorous, structured, non-visual way of writing.
And that raises a really important question for you to mull over. Why, in a course that's all about hardware and coding and getting a job, is there such an aggressive mandate on the documentation format? Why insist on LaTeX, which is explicitly not a what you see is what you get editor like MS Word?
Well, the core emphasis there is on rigorous, detailed documentation as an ongoing process. It's not just something you tack on at the end. Writing in a system like LaTeX, it requires a deep discipline, precise referencing, and an organization that mirrors high-level technical communication in the real world.
So think about that. If the project isn't considered complete without this incredibly disciplined documentation, it suggests that the final act of communicating your engineering process precisely and reliably is just as vital as the circuit you soldered.
Is the discipline of documentation the true final test of being a professional engineer? A thought for you to carry into your next design meeting. Thank you for joining us for the deep dive.
We'll see you next time.